Good. So welcome back, everyone. Today, our job is going to be to finish up chapter 19. There's really two more special types of reactions that I'd like to go over that still do fall into the category of nucleophiles adding to aldehydes and ketones. One of them involves a unique and intriguing phosphorus-containing reagent, and the other one involves conjugate additions. And yes, I've long since uploaded chapters 24 and 28. I did that during the week. I think that all happened during the week with the winter storm. So yes, those have been on YouTube for a while. And of course, today's will also go up probably today or tomorrow. I always try my best to get that done within a day. Clickers, please register your attendance. It will just be based on attendance, but I do have a little assignment for you guys to do that I think I'd like to do the Wittig reaction and say a few words about biological reducing agents and additions to carbonyl compounds. We'll do that first, and then we'll take a little break, and I'll let you take a look at that question. But other than that, we're just taking attendance. It's just free 100 out of 100 for attendance. Good. So the first special case of a nucleophilic addition to carbonyls is called the Wittig reaction. By the way, yet another pet peeve of mine. Please note there is no N in Wittig. W-I-T-T-I-G. It's not Witting, it's Wittig. So German name. So the Wittig reaction has been around for a long, long time. I can only tell you that it was already well established when I was in college, so call that the late 1980s. So you figure this thing's been around for like 50 or 60 years at least. And the Wittig reaction involves the addition of an intriguing phosphorus nucleophile to aldehydes and ketones. That nucleophile is known as a phosphorus irid, which is a strange word, Y-L-I-D-E. And the definition of an irid is what you see here. It's a zwitterion, and you learned the word zwitterion in Gen Chem. That's yet another one of those cases where if you took German in school as I did, or maybe spoke it at home, then you just won the internet. Because zwitterion comes from the German word Zwitter, which means twin. So it's a twin ion, but it's a special twin ion that has the plus and minus charges on adjacent atoms. So phosphorus ilids are actually resonance stabilized species. So again, this is not an equilibrium. It's a hybrid of those two structures. It's at all times a hybrid. But you could draw either of those two resonance forms. It doesn't matter. And R3 can vary. R3 can be pretty much any kind of alkyl group, and even some other functional groups will be tolerated. There's ester containing phosphorus ilids, for instance, and a lot of these, or at least a certain number of phosphorus ilids of this type, are available as shelf-stable reagents. Others need to be made from an SN2 reaction of triphenylphosphine with some alkyl halide, preferably primary. So that's just an SN2 reaction. We already know that mechanism. Followed by deprotonation with some strong base. Butyllithium is pretty common. Sodium amide is pretty common, NaNH2. And then you get your phosphorus ilid. So, but check that out. That's all in the textbook. Everything you'll need to know there. Bottom line is we're going to treat some aldehyde or ketone with a phosphorus ilid of this type, and so R1, R2, and R3 can vary. This does require an aprotic solvent because you do get a species that's essentially carbanion, so we can't have any protons around. But I'm even scared to use dichloromethane, though I know they often use that. THF and diethyl ether are very commonly used. Phosphorus ilids dissolved in THF, by the way, are especially dramatic. That solution tends to look like blood, so it's very intensely colored. In any case, these things react very straightforwardly with both aldehydes and ketones. the end result is a substitution reaction in which the oxygen of the carbonyl gets replaced by the hydrocarbon portion or the organic portion of the phosphorus ylide. And as an inorganic side product, you get triphenylphosphine oxide. By the way, don't just memorize PPH3. I expect you to recognize that the pHs are phenyl groups, they're benzene rings. So this is a big, bulky molecule, these phosphorus ylides of this type. And that's one of the drawbacks of this reaction. If we are at all interested in green chemistry, which I think we all are to some extent, regardless of political affiliation, let's say, I don't think there's anyone who says, yes, let's just make as much waste as we possibly can. You know, no one says that. Everyone's interested in being as unwasteful as possible. But that's one of the drawbacks is, if you work it out, triphenylphosphine oxide is a really big molecule. Its molecular weight has got to be upwards of 300. So it's a shame kind of tossing all that stuff out. And triphenylphosphine oxide is it's very hard to do anything with that. It's because it's so stable. And the reason for that is also the reason of the driving force of this reaction. It turns out that phosphorus and oxygen really, really like each other. So phosphorus-oxygen bonds are exceedingly strong. And that's the driving force of this reaction, is forming not one, but two phosphorus-oxygen bonds. Another problem, just in terms of my giving you some background to this reaction, it's what I have a little bit of experience with. I've done some Wittig reactions. In fact, I believe I have a paper with Dr. Singleton's group on that. I think my overall contribution to that paper was about this much. You know, I tried a few things, but I'll take what I can get. And we were looking at the mechanism of the reaction in some particularly strange and borderline cases. We're going to go over the mechanism that I think takes place in the vast majority of the cases. And the mechanism, I should say, has been hotly debated for a number of decades now. But in a moment, we'll go over what I think is the most reasonable mechanism for you guys to learn, the one that will certainly apply in the vast majority of cases. So what else? Oh, one other thing in terms of background. This triphenylphosphine oxide, in case you're wondering, is actually kind of a pain because it turns out to be at least a little bit soluble in almost everything. So it's very hard to get rid of. It can be done, though. You can, if you're careful with a column chromatography, which I don't know if you've done column chromatography in silica gel column chromatography in your organic lab yet. Actually, you probably have. I would hope that's one that they take care of in Organic 1 lab, along with all of the other sort of methods that you'll be using. So that's one way. There's also some recrystallizations that you can do, at least to an extent, if you're very careful with your solvent mixtures and do all the correct kind of voodoo things. You can have some success in crystallizing out the triphenylphosphine oxide. At least it's very highly crystalline. That's one good thing about it. But in general, you will wind up replacing the carbonyl oxygen with, again, the organic portion of the phosphorus ylide. You have the potential for E and Z isomers here. The phrasing of the question will let you know what to put. But there is that potential. In the example we're going to look at, I cleverly set it up so there's no issue here. There's only one possible alkene to come out. But in general, you could get it's at least possible that you could get a mixture of E and Z isomers. But other than that, this is probably, the Wittig reaction is probably the best method we have to date, at least as far as I know, of converting a carbon-oxygen bond to a carbon-carbon bond regiospecifically, which means that we know exactly where that change is going to take place. It's going to, the new carbon-carbon double bond is going to be exactly where the carbon-oxygen double bond used to be. And you can count on that with the Wittig reaction. It's very, very specific in those terms. So let's see. So like I said, the mechanism of this reaction has been under some debate to the point that I can tell you that the mechanism I learned when I was in college is different from the one I'm going to be teaching you guys. But my understanding is this mechanism has been experimentally shown to be the most reasonable one in the vast, vast majority of cases. The one I learned had actually 3 steps instead of 2 steps. But I believe it's generally agreed now that this first step is concerted, happens all in one step. I learned this mechanism as the phosphorus irid adds to the carbonyl and you get O-, which were in alkaline solution. That particular intermediate happens to be called a beta-ene. You can find all these words in the textbook. I don't think I care very much if you know them. And then the beta-ene closes that oxygen-phosphorus bond to make this 4-membered oxophosphetane, as it's called. But again, my understanding is at least in the overwhelming majority of cases, we go straight from the 2 starting materials to the oxophosphetane, all in one step. And this is one of those rare cases where you have a reaction proceeding through a 4-membered transition state. I think we can count on one hand the number of times we'll see a reaction with a 4-membered transition state, perhaps even half a hand. So this is one of those rare cases. And this is one way that you can draw the mechanism of that step. Again, I would say these dotted lines are optional. Some people like them, some find them to clutter the situation. So that's up to you, whether you draw the dotted lines. I have no preference either way. I tend to omit them, I guess, but I think I might sometimes draw them. They're fine. So that's up to you, whether you draw the dotted lines. I know there's some Chef John fans out there who watch him on YouTube, so you are the boss of your sauce. That's just you cooking. But be that as it may, this is only one way to draw that. Another way, again, you could use the other resonance form that has the minus charge in carbon and the plus charge in phosphorus. And again, these phosphonium ilids basically act as though they were carbanions. And indeed, you could show the carbanion adding to the carbonyl carbon, just like it would if it were a Grignard reagent or an organolithium. And then you would still show the electrons in the carbon-oxygen pi bond swinging out to form that, all-important oxygen-phosphorus bond. So that's why we actually get a 4-membered transition state and then formation of a 4-membered intermediates like this. That's vanishingly rare that this type of thing will actually happen. But again, the driving force is forming that oxygen-phosphorus bond. So that type of bond is so tremendously favorable to form that we will even go through a 4-membered transition state to a 4-membered intermediate. This so-called oxophosphetane, again, is pretty unstable, as you can imagine. And that falls apart in, again, a concerted step. If in case you're curious, I don't really care if you know this, but this could be called a 2+2 cycloaddition, in case you're curious. It's kind of like a Diels-Alder reaction, except where the Diels-Alder reaction is a 4+2 reaction, right? You've got 4 electrons in your diene reacting with 2 electrons in your dienophile. This is a 2+2 cycloaddition. So again, I don't really care if you guys know that. I'm just letting you know in case, because I know there's always people who are curious what these things are called. And this here would then be a 2+2 cycloreversion. So we're going to break open the 4-membered ring, which is favorable in and of itself, as you can imagine. And as if that weren't enough, we form another oxygen-phosphorus bond. So in so doing, we will lose triphenylphosphine oxide as our as a side product. That's going to be something that we'll have to take some pains to remove from the reaction mixture. But in the end, the major organic product will be the alkene. And as you see in this case, I cleverly picked a starting material so that there's no cis and trans possibility. There's only one possible alkene product. course, it doesn't matter which direction you draw the phenyl group, right? There's no cis-trans distinction in this case. The best advice I can give you in order to learn what you need to know will be, again, what we covered in chapter 8. So please go refer back to that if you want to see a method in terms of what you should do in order to know what you'll need to know for the next exam, which is make up your own aldehydes and ketones, make up your own phosphorus ilids, change out that R group for something else. I don't even suppose that really has to be a hydrogen there, although it normally is, but it doesn't have to be. But make up aldehydes and ketones, make up phosphorus ilids, get with a classmate, boyfriend, girlfriend, best friend, worst friend, mother, father, aunt, uncle, cat, dog, etc., and make up compounds for each other to work it out, figure out what the, draw the mechanism and figure out what the structure of the product will look like. But I think this is the most reasonable mechanism for you guys to learn. Based on what I've seen, it's pretty well agreed experimentally that this is a two-step process. Again, in the vast, vast majority of the cases. Good, and I think that's about all I can think of to say about that. Questions on the Wittig reaction or on its mechanism? Looks like I did it again. Maybe even Bella could have handled that. Good. Well, let's see. Where does the O go? Good. The oxygen in the carbonyl winds up in the triphenylphosphine oxide side product. So it's sort of like the organic portion of the phosphorus ylid and the oxygen wind up switching places, right? Instead of a carbon-oxygen double bond, you get a carbon-carbon double bond. And what used to be the oxygen in the carbonyl winds up in the triphenylphosphine oxide. No, those are good questions. You want to be asking, in terms of mass balance, where does everything go? Perfectly good question. Good. So like I said, this is probably the best reaction we have to date as to making a carbon-oxygen double bond into a carbon-carbon double bond regiospecifically. Why is the phosphorus-oxygen bond so strong? I don't know that I have a ready answer right off the top of my head. My instinct would be that it would have something to do with the electronegativity difference between oxygen and phosphorus. I think another reason is that phosphorus can become, I think the electronegativity difference is just right. That's, again, just an instinct I have. Another thing is, of course, with phosphorus, remember that elements in the third row of the periodic table and below can become hypervalent. So you can actually form another phosphorus-oxygen bond here. That would not be available if this were a nitrogen. You wouldn't be able to form a fifth bond. But since you can here, I feel like that has something to do with it. So I'd have to, dig around and do some research in order to find a better, more complete answer than that. But that's off the top of my head, I would say that's the best I can do. I feel that the electronegativity difference is just right in order to form very strong bonds. And again, the ability for oxygen to go hypervalent and take on 10 electrons around it, I think that only helps in this situation. Are there other kinds of ilids? Yes, there are. Ilids involving sulfur are also known. Of course, sulfur can also become hypervalent. There are nitrogen ilids as well, but they're kind of boutique. They don't show up as much. Again, because nitrogen cannot become hypervalent. So they're used for some things, but they're of limited use, I would say. Using phosphorus ilids is much more general, as far as I know, based on such experience as I have in organic synthesis. So sorry I couldn't give you a better answer, but that's about the best I can do just off the top of my head. It's a perfectly good question, though. Good. Other questions about the Wittig reaction? Well, again, I'm taking you through kind of this section in biological reductions. Again, biology is not a prerequisite for this course. I mean, except insofar as I believe a term of biology is required in order to get a high school degree. So beyond that, it's not required for this course. And in terms of this chapter, of course, I don't expect you guys to memorize any of these reactions, but I think it's worth your having heard that there are biological reducing agents based in the nicotinamide dinucleotide. These things, by the way, of course, look like nucleotides. In fact, they pretty much are, which are a subject in chapter 28, which is fair game for the next exam. But there are two that are based on the nicotinamide dinucleotide, NADH and NADPH. These two reducing agents tend to be kind of like sodium borohydride or lithium aluminum hydride. They tend to take the place of those hydride reagents in biological systems. And then there's also the flavonoadenine dinucleotide system, FAD and FADH2. FADH2 is the reduced form. And this guy tends to be kind of like unto hydrogen over palladium catalyst. There are notable exceptions to this. There's a red flag going up in my head that there's a major exception which we'll actually encounter when we get to chapter 29, which is going to be on metabolism. Of course, our goal here is not going to be memorizing these biological pathways as such, but I'm sure I'll point that out when we get to that. So our goal is not going to be to memorize those things. Those of you going on to biochem, which I recognize is not all of you, but those of you going on to biochem probably will have that pleasure of flat out memorizing all of these different biological pathways, what your Krebs cycle, your glycolysis, all of these things. We're not going to be concerned with memorizing them as such, but I do still think it's worth pointing out that these you to memorize as an intra-bio. I'm not surprised. And you'll probably have to do those again, those of you going on to biochem. Not here. We're not going to be interested in just flat out memorizing those. Be that as it may, I think it's worth pointing out that these are just some examples of reactions that can involve nucleophilic addition to carbonyls. And there are other types of nucleophilic addition to carbonyls as well that we'll get to when we study those pathways later on in chapter 29. So the only point, the major point at least that I would say of section 12 of this chapter is that, these things go on in living systems as well. These aren't just sort of this abstract thing that is no bearing on reality. There are reduction reactions and other addition reactions to carbonyl compounds, like unto the ones, maybe not so much the Wittig reaction, but like unto the ones that we covered before these, that you will run into in your biology classes. So this is not just sort of like a mental game that we play only for organic chemistry. These things do happen in living systems as well as in reactions that are relevant to making polymers, to making other materials. So we'll get to that as well. And as I said, when we finally get to chapter 31, which we will on our very last class day, that's going to be when, as it were, we throw a bone to all y'all who are, a term, by the way, this displaced New Jersey boy has learned as a result of being in Texas. It's a very useful term because it's the plural that we don't really have in English. But anyway, as that will be the day for all y'all engineering and sort of material science types. That's your special day, the last day of class. Good. So the only other thing that I would like to go over today is this issue of conjugate additions, which are also called Michael additions, just like the name. Well, this person's last name was Michael. They're also called 1,4 additions. There you go. 3 different names for the exact same reaction. I'd like to go over that after we do our clicker session. So again, today is a freebie, just based on attendance. So please do register your attendance. But your goal today, your mission, should you choose to accept it, which by being in this class, you've tacitly accepted it, is something we talked about the other day. We talked about the formation of acetals, such as this cyclic acetal here, and we said this goes through a hemiacetal intermediate and then reacts further to lose a molecule of water and give you the full acetal. But I did point out that you can make cyclic acetals of this type as long as you're able to close, I would say, a 5 or 6 membered ring. 4-membered ring, not so much, 7-membered ring, not so much, but 5 and 6-membered rings, you're good to go. And so if we used, for instance, a diol like ethylene glycol, which is this one here. Ethylene glycol is the trivial name for 1,2-ethane diol. You could also do this with 1,3-propane triol, which just is an extra CH2 here. In that case, you would get a 6-membered cyclic acetal rather than 5-membered. So your mission is to come up with a reasonable mechanism for this particular case. Good, so hopefully with our first step, we're protonating that carbonyl oxygen. That's commonplace when we're under acidic conditions, which you can tell based on what you're given. There's going to be an acid catalyst in addition to our ethylene glycol, where ethylene glycol is going to be essentially our solvent. And so in order to put that proton on, we'll use, again, the conjugate acid of the ethylene glycol. Of course, we wouldn't want to use both oxygens protonated. That doesn't really, it's not very reasonable to have an intermediate, to have a species with a +2 charge. Why would we do that instead of protonating 2 different molecules once? I think that makes a lot more sense. So, inevitable question, would you lose points for having the double conjugate acid? Yes. It wouldn't be 1,000 points, but that would not be perfect. That would not be the ideal way of writing it. I think it makes the most sense to write it like that. So that protonates our carbonyl oxygen, which again we want to do because otherwise, if we have just straight nucleophilic addition immediately to the carbonyl, you'll get an alkoxide ion. You'll get a species with a minus charge in oxygen. That does not make sense in acidic medium. So that's why we tend to protonate carbonyl oxygens before that in reactions in acidic medium to avoid getting a strongly alkaline species that does not make sense to invoke it in an acidic medium. So then you can have your nucleophilic addition. Looks exactly the same as if this were a simple alcohol like ethanol or methanol, except of course that, who's there? Bella. Except of course that that you have a diol. So that would add in exactly the same way, same exact mechanism. And it's at this point that we want to have a couple of proton transfers. Again, those proton transfers are very, very common in acidic medium. The idea being to avoid, again, invoking any strongly alkaline intermediates. So it's quite common to have these proton transfers, especially in acidic medium. So we'll use, again, a diol molecule in this case to pull off that proton, not H2O, right? When we look at what we're given, we're not given water. I don't see H2O or H3O plus mentioned. So we want to avoid using any species that don't make sense. So we'll use an alcohol molecule to pull off that proton, and then we'll use, again, the conjugate acid of the diol, which it might not be the exact same one that we just protonated over here. It could be a different molecule. Doesn't really matter, but we'll do that to protonate our oxygen over here. This will be so we can lose a molecule of water as a leaving group. So once we've done that, we will do exactly that, just as we did in the reaction before. So far, by the way, the mechanism is absolutely identical to what we had before when we were forming a non-cyclic acetal. We'll lose this molecule of water, and if you want to, you can show this other oxygen helping by forming a carbon-oxygen pi bond. I would call that arrow optional. If you don't draw it, then you're simply using the other resonance form here. So you would have both lone pairs still in the oxygen and the plus charge in carbon instead of an oxygen. And remember, with a resonance stabilized intermediate, it does not matter which resonance form you use. You will be able to draw a correct mechanism with any of the resonance forms. It's always possible to draw a correct mechanism either way. So this is now the only difference between this mechanism and the one we did earlier with an acyclic acetal formation, is that now we're set up to form a 5 or 6 membered ring. And so that, of course, is very, very favorable entropically. We don't need to invoke a molecule coming from outside the system. We can do an intramolecular reaction. And always when given a choice, if you have a choice between an intramolecular reaction and the equivalent intermolecular reaction, we will favor that intramolecular reaction, particularly when we're forming a 5 or 6 membered ring. Because again, with a 4-membered transition state, those are rare, that's not so good. But 5 or 6 membered transition states are very common because everything's in exactly the right place. It's easy to close a 5 or 6 membered ring, much more so than a 4-membered ring, certainly, even much more so than a 7-membered ring. Anything bigger than a 6-membered ring, now it tends to be too big. Everything's flopping around all over the place, and it's hard to get the 2 reacting centers to be nearby each other in space. But 5 and 6-membered rings are just right, and this is not the only case we'll run into with the 5 or 6-membered transition state. So this is the exact same type of reaction, except it's not an additional water or not an additional alcohol molecule. This happens in the same reaction mixture. So we close that 5-membered ring, and now all we need to do is pull off that proton in order to get a neutral product. We will again use a molecule of our diol in order to do that. And then we have our cyclic acetal product. So it's very easy to make 5 and 6-membered cyclic acetals. Mechanism's essentially identical. What was I going to say? And again, we won't use any water molecules. Yes, we do technically generate 1 molecule of water here, but we've covered this type of thing before. Remember, this water molecule is now going to drown in this ocean of ethylene glycol, which is effectively our solvent. And it's as though the water were removed from the solution. You know, if you have 1 molecule for every 10 to the 19th or 20th power ethylene glycol molecules, then water is a non-factor here. It doesn't make sense to use it in the mechanism. So, but I hope you can convince yourselves that this mechanism is very much equivalent to the one we learned just for forming an acyclic acetal. What else was I going to say? Oh, crap. I know I had some other point. Maybe it'll occur to me. But it's very much the same type of mechanism. The only difference is we've got an intramolecular step. Oh, I know one thing I was certainly going to say. It's at this step that a lot of students make a mistake. They try to combine these 2 steps into one. They feel they can just use the electrons on this OH and just do an SN2 reaction to get rid of water. But that's not reasonable because I think you'll agree in general, this carbon's going to be much too crowded to have an SN2 type of reaction. Much easier to use the other oxygen to help kick out the water molecule and get this type of intermediate. Especially, I think you'll see that intermediate looks very much like the corresponding intermediate in the acyclic case. So yeah, I think that's about right. Good, I think that's all I can think of to say about that. So this thing, including the answer, will be up on eCampus. I would say either tomorrow or the next day, or rather today or tomorrow. I usually try to get those done within 24 hours. Good, so you can refer to that on eCampus. Along with, I might have mentioned, I've got about maybe 4, maybe 5 other older brief sessions that we missed, either because we ran out of time or from the winter storm. So I'll try to get those all up sometime today or tomorrow. Good, well, we have only one other type of reaction to go over, which is the so-called conjugate addition, also called a 1,4 addition, also called a Michael addition. So there you go, there's 3 different names for the exact same thing. And the idea here is that we've seen nucleophiles that like to add directly to the carbonyl. That would include Grignard reagents, alkylithium hydride reduction reagents for sure. But when you've got a so-called alpha beta unsaturated ketone or aldehyde, then you've got the potential for other options. And I'm giving the definition of the alpha and beta carbons and an alpha beta unsaturated aldehyde or ketone. That definition is here in the class notes, where you can use this structure as the definition here. And it turns out there are certain nucleophiles, including water, including the cyanide ion, including primary and secondary amines, cuprates. There are one or two others as well. These are all listed in the textbook. That if your electrophile has an alkene carbon-carbon double bond conjugated to the carbonyl, then those nucleophiles will add preferentially to the beta carbon rather than directly to the carbonyl. What if there is no alkene conjugated to the carbonyl? Well, then all of these nucleophiles will add straight to the carbonyl carbon. And we've talked about these already. Cyanide ion making cyanohydrins, primary and secondary amines making imines and enamines respectively. Cuprates we've discussed, and enolates we'll get to in a later chapter. So this decision that we have to make occurs only if there's an alkene carbon-carbon double bond conjugated to the carbonyl carbon. If there's no such alkene, then there's no issue. All of those nucleophiles will do a direct addition to the carbonyl. But if there is an alkene that's conjugated to the carbonyl, then these reagents, these are only some of them, there are others as well. Those types of nucleophiles will now prefer to add to the beta carbon of the alpha beta unsaturated system. So it's that one that we need to end off this chapter with. And I have an example here in your class notes. Here I'm using 2-cyclohexenone as our alpha beta unsaturated ketone or aldehyde, which is commercially available. You can get your hands on that stuff. And I'm using methylamine as an example of a nucleophile that you'll see is mentioned in the list of nucleophiles that prefer to add in a conjugate fashion given the choice. If that carbon-carbon double bond weren't there, then of course the methylamine would add to the carbonyl as usual and you'll get the imine. So we've already gone over that mechanism. But if you have an alkene conjugated to that carbonyl, then the nucleophile prefers to add to the beta carbon. And the mechanism of such a conjugate addition is given here. Of course, being in an acidic solution, you will first protonate the carbonyl oxygen. That's pretty common. Again, we don't use an H3O plus molecule. Why? Because when we look at what we're given, we don't see water mentioned. It doesn't say H2O, it doesn't say H3O plus. So this is going to be done under anhydrous conditions. So once we've done that, rather than our amine, our primary amine adding directly to the carbonyl, since we have this alkene here, so you have to look at the structure of the organic starting material. Is there an alkene conjugated to the carbonyl? If not, then you just get direct addition and we'll make an imine like we talked about last week. But since there is an alkene here, our amine will add to the beta carbon and we will shift those electrons in so as to get rid of the plus charge in this oxygen. Then, as so often happens, we've got a couple of proton transfers. First, we want to remove a proton from this nitrogen. We'll use our amine in order to do that, not a water molecule. Again, we're not given water, so we can't use that. We're under anhydrous conditions. And then we'll immediately use the conjugate acid of the amine that we're given in order to go to essentially what is the protonated product. This will also tautomerize this enol to the keto form. We've talked about that type of tautomerization a little bit. There's actually a whole chapter based on enol forms, essentially, enols and enolates. So that comes later. But we've talked about this a little bit. So we'll use, again, the conjugate acid of the amine in order to do that. At that point, you've got your, essentially your product, but protonated. So we'll just use our amine in order to pull that proton off. Again, we're not given water, So we can't use H2O or H3O plus. We got to use what we're given. And so this amine pulls off that proton, and then we're done. And I think in this reaction, that reminds me what I was going to say, as well as with forming an acetal, whether cyclic or otherwise. It would not be a waste of your time to convince yourself that these are both acid catalyzed. So we don't generate any new H plus ions, nor do we consume. So of course, I think we would want to start by protonating our carbonyl oxygen. And now we also need to figure out what is going to be our source of acid. Again, this is done under anhydrous conditions, at least in this case. Which we can know based on, looking at what it is that we're given. There's no water mentioned. So we're going to have, instead of H3O plus, we'll use the conjugate base of,
right now. I'll eat my lunch first.
of ethanol. Since, again, there is no H3O plus, not in any reasonable quantities anyway. So I would expect the first step of the mechanism to look very much like always. We use our electron pair on the carbonyl oxygen in order to pick up a proton from the conjugate acid of the solvent. And so I would, at any rate, would predict that our intermediate would look a little something like that. Now this is ready for addition. If this will work, let me see if it lets me put electron pairs in that oxygen. Oh, okay, ChemDraw has gotten smarter over the years. So there's our ethanol. And again, notice we'll use an ethanol molecule, not ethoxide ion. We don't use ethoxide ion. How do we know? Because when we look at what we're given, there's no ETO minus mentioned, nor are you going to get any ETO minus in acidic solution. Alkaline solution, yes, though these don't tend to work so well in alkaline solution. But an acidic solution, which we can tell we're in based on what we're given, no way. Remember, alcohols are very, very, very weakly acidic. You're not going to have any reasonable amount of the ethoxide ion present. Ethanol and other simple alcohols like that have pKa's of maybe around what, 18 or 19, something like that. So there's not going to be any of that around. I mention that because it's a very common mistake, because students perceive that if they use ETO minus here, they'll save themselves a step, which would be great if it comported with reality, but it doesn't. So we need to use species that make sense based on what we're given. So our ethanol is going to attack now in the beta position, since that's going to be one of your nucleophiles that prefers to attack in that manner, given the choice, and here it is given the choice. So I would expect the mechanism of that step to look something like this. We need to pull that proton off. I would use another ethanol molecule to do that. And that's just so we have, to get rid of the plus charge so we can continue to push the reaction forward. Once we've done that, then we will have that intermediate. So now all we need to do is tautomerize the enol to the keto form. Again, we're going to need to put on a proton. And actually, I already have one of those species up here. So once again, we'll want to use one of these conjugate acid molecules of our solvent, in this case, ethanol. That's one way of drawing this mechanism. Again, it's not wrong to leave off this arrow. You'll only wind up with the other resonance contributor. It doesn't really matter which you use. Both are perfectly correct. And then, of course, we have our Last but not least, we'll use our solvent molecule, in this case ethanol, to pull off that proton. And then we'll be done. That gives us our neutral product. Good, so sorry for keeping you a little bit long. But with that, we're essentially done. And I think if you compare to what we did with that primary amine just recently, you'll see it's the same thing. Other than that, I'm over time, so have a great day. We will see you all on Wednesday.